So today's podcast has to do with calorimetry, and calorimetry is a great way. It's actually the way they find out how many calories in food. So we're at Rebel Donuts, and it is in Albuquerque, but I mean, as you see the donuts, they're beautiful donuts. But basically, you'd use a bomb calorimeter, stick a donut in a cool device, basically have it explode, put it in oxygen, light a match, it explodes, its heat is released to water, and you find out how much water, or how much heat the water absorbs, and that tells you how much heat the donut lost, and tells you how many calories were in it.
Point it at me when you're done.
Alright, so with this podcast, we're going to start off with what's called the First Law of Thermodynamics. Alright, First Law of Thermo. Now, First Law of Thermo basically says that energy, we're going to use capital E, energy is neither created nor destroyed. And because of Einstein's excellent equation, E equals mc squared, you may have heard this also termed matter is neither created nor destroyed. And because matter and energy somehow have this relationship through Einstein's equation, this is also true. Okay? So if we have some kind of equation, because heat is a type of energy, we can always say that Q, alright, equals Q. And this can be the system, and this can be the surrounding, okay, just arbitrarily. So energy equals energy. However, if the system is losing energy, what's happening to the surroundings? They are gaining energy. What's happening if the system is gaining energy? It must be that the surroundings are losing energy. So because it's neither created nor destroyed, this relationship is always true. The Q equals negative Q, alright? So if the systems are gaining, it means the surroundings are losing, and vice versa. It really doesn't matter where that goes, but one side of every equation is going to have a negative in front of it. So typically we measure heat with the equation Q equals mc delta T. So we're really going to have mc delta T of system equals negative mc delta T of surroundings. So because water is so good at absorbing energy and has such a high heat capacity, if we have a reaction that we can react that gives off heat to water, it's very easy for us to measure. Just put a thermometer in water and accurately measure what mass of water we have. We know the specific heat of water. So if we know how much the water changes, we can find out how much our system is releasing. And if we know the mass of our system, we can calculate its specific heat capacity, or vice versa. Alright? So again, first law of thermo, energy is neither created nor destroyed, which leads us to the equation Q equals Q. Because in a system, energy is being transferred. Something's losing it, something's gaining it. So really Q equals negative Q. And because Q is something that we can't really measure specifically, but if we know the mass, the specific heat, and the change in temperature, we can calculate Q. We can really set the equation mc delta T equals negative mc delta T. Alright? The last thing you need to know is what's known as thermal equilibrium. And thermal equilibrium is simply if we put two things at very different temperatures together, after a certain amount of time, they will come to the same temperature.
Alright class, it is a cold day outside. My kids are playing in the snow. And I'm inside, thinking I might make myself some hot chocolate because it looks really cold out there. So, here we are in my kitchen, and I've got some hot chocolate mix. I pour this in the mug. I don't know how much to put in there. That looks like plenty. And if it's real hot chocolate, we don't use water, we use milk. Milk. Stir that up a little bit. I may have used too much powder, but that makes it all the more chocolatey.
So anyways, here we go. We're mixing. Woo, making a mess. All right. And we're going to pop it in the microwave real quickly. So, I don't know, minute? Sure. Alrighty. Take this out. Give it a little stir. Ah, this is going to be delicious. Oh, that's hot. Chocolatey though, but it's hot. I'm going to let it just sit there and cool for a little bit, I think. Alright, so I figured I wouldn't just let the kids play outside, but I would get some work done, so I shoveled the driveway. Nice, now I'm going to go get that hot chocolate. Oh boy, this will be so refreshing. Have a nice warm mug of hot chocolate. It's not really that warm anymore. It's kind of cool. It's a good thing we have microwaves though. Right. So thermal equilibrium means that T final for two substances, for two let's call it substances, is the same. Because when we put them together, they'll eventually come to some kind of temperature between what they both started at. So if we know the final temperature of water, that is also the final temperature of our metal. If we know the final temperature of the metal, that's also the final temperature of the water. All right. So again, typically, MC delta T will be some kind of metal. Is what we're going to do in our class in general chemistry. We're going to have a lab where we take a piece of metal and heat it up, and then surroundings are typically the water. All right. Again, thermal equilibrium T final for two substances is the same. So notice we have a delta T on the left, which is T final minus T initial. We have a delta T on the right, which is T final T initial. Those two T finals are the same exact temperature. All right, and that's notes for calorimetry.